So you have this exchange via diffusion, but there's also another means which is called the bulk flow. First of all, what is bulk flow? That's when all the components of a particular solution or a particular liquid are flowing together. In other words, if I had a glass of lemonade here and I'm sipping it through a straw, it wouldn't be, okay, here comes the water, then the sugar, then the lemon juice. It's all coming together, right? That's all I mean by bulk flow, all right? So what we see at the level of the capillaries is we're going to have a movement of all the plasma out, okay? That's bulk flow out. But you have to underline this as an exception, except the plasma proteins. They should not be part of the bulk flow. They shouldn't be able to fit out the pores, okay? Movement in a bulk flow manner out of the capillaries is called filtration. Some books call it ultrafiltration, but your book calls it filtration, so we're going to stick with that. So that's the movement of everything except for the plasma proteins out of the capillaries. And bulk flow back in is called reabsorption. All right? So remember we talked about the fluid outside of the cell here, outside of the capillaries, is called, interstitial fluid. And that basically, now I can state, and you can see it, that that's going to be basically identical to the plasma, right? Except for the plasma proteins. So in other words, we have mechanisms to regulate the composition of the blood directly, but because of this bulk flow, aren't we regulating the composition of the interstitial fluid also? Okay? All right, so we're talking about bulk flow. Now we're going to talk about what determines bulk flow, and there's going to be several things important here. Okay. All right, we're going to be, when I'm doing this, remember that person who had a blood pressure of 120 over 80? We calculated the mean arterial pressure of that person equals 93 millimeters of mercury. All right, and remember I also talked about there has to be a pressure gradient. Pressure has to keep falling in order for flow, right? From the arteries, arterioles, capillaries, to veins, all right? The pressure when the blood is being returned to the heart in the veins should be close to 0, all right? So what is the pressure of the capillaries? By the time the blood is entering the capillaries, for this particular person, the pressure will have fallen to about 37. Okay? It's good. Yes?
On the exam, are you going to give us like a certain mean arterial pressure and we have to...
No. On the exam, and I told you this before, I'm going to give you somebody's blood pressure. I could ask what's the systolic versus what's the diastolic. I could ask you the pulse pressure. Remember, that's the difference between the two. And I could ask you to calculate the mean arterial blood pressure. All right? But I'm not going to say, because a person's mean arterial blood pressure is this, what is the pressure here?
So the exam that will be given?
Yes. Okay, that will be given. Okay. And by the time towards the end of the capillary, the capillary blood pressure will have fallen to around 17. Okay, so this is going to be our first determinant of bulk flow, capillary blood pressure. Okay, so let's put some pores here. All right, throw some plasma proteins in here. right? Because they should not be part of the bulk flow. So, determinants of bulk flow. Capillary blood pressure. Knowing what you know, do you think the capillary blood pressure, the pressure inside the capillary, is going to favor filtration, which would be bulk flow out, or reabsorption, which would be bulk flow in?
Filtration.
Filtration, does that make sense? The pressure in is pushing out. And I gave you the example, if you have a hose and water is running through it, if you poke a hole in it, water is going to go out, right? The pressure in pushing out. So, capillary blood pressure favors filtration. So I just want to write that here, and we'll see why it leads to filtration. Okay, so these are the determinants of bulk flow. The next determinant is called plasma protein colloid osmotic pressure. Plasma protein colloid osmotic pressure. Okay, this is the pressure exerted by these proteins, the plasma proteins, which under normal circumstances should not be able to get out, okay? So now you have to go back and think of osmosis. So if I have a membrane here, this membrane, I'm going to tell you, is permeable to water, but not to the solute I'm going to put in. So I'm going to put some solute in to side B. Which way are you going to get a net movement of water? A to B. Does everybody agree with that? Right? There's more water on this side, so you're going to get a net movement of water towards where there's more solute. And I always gave you that example of salt on a slug, right? You put salt on a slug, which you are never going to do. The slug will dry out because water will leave it. It's going to the solute, right? Okay. Knowing that, do you think plasma protein colloid osmotic pressure favors filtration or reabsorption?
Reabsorption.
Reabsorption, right? It's just water going from here to here, water going from here to here. Okay, so this favors, reabsorption, and I'm going to give you this number, a normal number here would be 25 millimeters of mercury, okay? The third determinant is called interstitial fluid hydrostatic pressure. Okay, out here is the interstitial fluid. It is a fluid, therefore it exerts a fluid pressure, hydrostatic pressure, all right? It's not very much. It's only, so interstitial fluid hydrostatic pressure, it's only around 1 millimeter of mercury. It's the pressure out. Do you think that is favoring filtration or reabsorption?
What does it stand for again?
Interstitial fluid hydrostatic pressure. Hydrostatic pressure.
It should favor reabsorption?
Right, it's the pressure out here, so it's pushing back, right? So this favors reabsorption. And it's just like if you go back to that hose analogy, if I have a hose, right, and I have water running through it, and I put it in a bathtub filled with water, so I'll call that bathtub water hydrostatic pressure. Isn't that going to be exerting a pressure pushing back? It's not going to win, right? But it's still a pressure. Okay, so look at what we have here. We have favoring reabsorption, which is bulk flow in, 25 and 1, so we have 26. So let's just, that under normal circumstances doesn't change. So let's write a bunch of these 26s here to indicate that it doesn't change. All right? That's favoring bulk flow in, reabsorption. All right, but what is the pressure we have here? Capillary blood pressure, pressure in is pushing out, so it's favoring filtration. But that keeps dropping, and these are just two snapshots, 37 and 17. In other words, it doesn't go 37 to 17 in one, it just keeps falling. Everybody understand that? So let's just write some numbers here. 33, 30, 27, 24, 20. Okay? All right. Here the pressure is 37. Here it's 26. Who's going to win? If we're going to have net filtration or net reabsorption? Think about it.
Filtration.
Right, 37 is higher. Thank you. 37 is higher than 26, so here you're going to have net filtration. 33 is still higher. 30 is still higher. 27 is still higher. But as soon as the pressure in the capillary falls below the pressure pushing back in, this 26, then you get net reabsorption. Okay? So you have this constant movement, all right? But at the beginning, it's net filtration. At the end, it's net reabsorption. Okay? Okay. Now, there is another pressure called interstitial fluid osmotic pressure. Now, so let's write that over here. But I'm going to put an asterisk next to it, and I'll tell you why in a second. So, interstitial fluid osmotic pressure. This should normally only be about 0. All right? All right, osmotic pressure. Which side over here, A or B, has a higher osmotic pressure? B, right? Water will move there. There's going to be a net movement of water there. All right. Normally, there's not going to be plasma proteins out here. But every once in a while, and there's under some normal circumstances, plasma proteins will be out here. If they do go out there, they're going to exert a pressure. Okay? And that pressure is going to favor filtration, but normally that doesn't happen. That's part of a response we'll talk about later, or it could be, in pathological. All right. Now, if somebody's arterial blood pressure was changing, all right, so I'm going to leave that up. You'll see why in a minute. So now we're going to go back and see how this capillary blood pressure, so the question you can put, how does capillary blood pressure affect arterial blood pressure? Okay. So we'll go back to that person who had a mean arterial blood pressure of 93. Okay. Now maybe that person was in an accident and the person is bleeding. And say that person's blood pressure was falling. Okay? A drop in arterial blood pressure. Would this number 37 be 37 anymore? No, there's less blood, so the pressure would be lower. So a drop in, let's write that over here, low arterial, I'm just writing this out to distinguish this, low arterial pressure is going to ultimately lead to a drop in capillary blood pressure. Okay? So let's indicate that here. Let's just drop this to 33, right? All right, you're going to still have some net filtration out, but aren't we going to get, to 25 much quicker? All right, so what happens is, this is an automatic temporary thing, which occurs, and it ultimately is going to help to get the arterial blood pressure back up. Because if you have less filtration, you're going to be returning more blood to the heart, right? That will increase cardiac output, and more blood will enter the arteries.
It's good to go.
Hello, come on in, just finishing up this, okay? Does that make sense to you? And the same thing if somebody's arterial blood pressure was increasing, that would increase the capillary blood
I
pressure.
got one more.
I have to just sit here and I'm just finishing up. I just have about 5 more minutes left. Okay? Does that make sense?
Go over one more time.
Okay, just, all right. Let's do, say somebody's in an accident. I was asked to do this one more time, so I'm going to. Say if somebody was in an accident, they're bleeding. That is going to cause a drop in their blood pressure, right, in the arteries. So if their mean arterial blood pressure is not going to be 93 anymore, right, it's going to be lower than 93. Therefore, the pressure entering the capillaries is going to be lower all throughout them, right? So the pressure, which determines filtration, this is physiology, you don't have to worry about this. We're almost done. But it is fun, right? Okay. There's going to be less pressure for filtration. So you're going to get less blood moving out, right? Therefore, more blood is going to be returned to the heart. Therefore, that will increase cardiac output. And cardiac output is into the arteries, so that will help get the blood pressure back up.
So a decrease in arterial pressure leads to the increase of capillary.
No, it leads to a decrease in capillary pressure, which ultimately is going to lead to an increase in arterial blood pressure. And again, it depends on the extent of the bleeding or, the drop or what the problem was that caused this in the first place. Okay? All right. Now, what? We just did that, all flowing changes in mean arterial blood pressure. And then finally, the last thing that I'm going to discuss is edema. And edema is excess interstitial fluid. So there's going to be a swelling, right? So what causes edema? One of the causes of edema is liver disease. Why would liver disease cause edema?
Because you're not making enough plasma proteins.
Exactly. If somebody's liver is diseased, remember those plasma proteins were supposed to be made in the liver. So the liver there's something wrong with it, it's not going to be making as many plasma proteins. And of this 26, 25 of this was from the presence of the plasma proteins for reabsorption, remember? So if you have less plasma proteins, you're going to get less reabsorption and you're going to have an excess interstitial fluid. Does that make sense? Okay? So you can see all these things in the body are very interconnected. Kidney disease is another problem that can cause edema. We didn't do the urinary system yet, but you're going to see normally we should not be losing plasma proteins with the urine. All right, if somebody gets their urine tested, there shouldn't be plasma proteins in there. But with certain kidney diseases, plasma proteins are lost. Again, you go back, 25 of this 26, this pressure favoring reabsorption, was from the plasma proteins. If there's not enough, you won't get enough reabsorption. And finally, burns. With severe burns, people lose plasma proteins. So along with all their other problems that they have because of the burns, they're going to be swollen also. Yes.
How does kidney disease affect,
Kidney disease, yeah.
the pressure?
Because with kidney disease, certain kidney diseases, you lose your plasma proteins in the urine. So anything that causes you to lose plasma proteins is going to result in less pressure for reabsorption, more fluid gets stuck out here, and you get swollen. And this, all these can be pretty dramatic, you know, really, you know, a lot of pressure. Okay, we have now completed last Thursday's lecture.